Hello everyone, Richard Walding here. I'm just going to run through a prac I think you might find useful for senior physics. So let's get started. Now the prac itself I'm calling magnetic field strength and distance between two magnets. Okay, there's a little picture on the screen of the apparatus I'm going to use. But firstly, let's talk about the existing pracs in senior physics. Now the first one is this one here. It's called the strength of a magnet at various distances. Now that word, this is straight out of the Queensland physics syllabus. The word strength is a bit tricky because it could mean the force between two magnets, and that's how I've interpreted it here. You'll see the page out of my Oxford physics book, and I've just got two little magnets and separated with a ruler measuring the separation distance, and one resting on a electronic balance. Okay, so that's measuring the force between two magnets. So I'm interpreting that word strength as meaning force. But you could also interpret it as the magnetic field strength or the flux density of a magnet at various distances. Okay, so here's just an image of a girl in one of my classes measuring the distance between the two magnets. You can see her there with the vernier calipers and the electronic balance and so on. So that's a nice little prac. Now that's one of the mandatory ones in Queensland. The other one is this one here, straight out of the syllabus, or the heading is, an experiment to investigate the force acting on a current on a conductor. That's a current carrying wire basically in a magnetic field. And here's the page out of my book, and you'll notice you've just got two magnets with a wire running between them. You pass a current through the wire, and there's an interaction between the field, magnetic field, and the wire, or the magnetic field produced in the wire, and that can be registered on a scale balance. Okay, the apparatus I use in senior physics is just a piece of bent copper wire with two little rare earth magnets here either side of an aluminium channel. They hold themselves together because of the force and the friction. Run a current through it, and it pushes down on the scale pan, and that's registered as a scale reading on the balance. Okay, so we can modify those two, either of those two, or both of them if you like at the same time. But basically, I'm going to talk about how we can modify this prac by looking at the field strength, not just in the middle and varying the current, but keeping the current the same and varying the position of the wire in the magnetic field. Okay, so let's have a look at the logic behind this. Oh, by the way, that's the cover of the physics text that I took those images out of. There's my chapter 15, which has all the pracs, all the mandatory pracs anyway. The workbook has the suggested pracs. Okay, so let's have a look at what we can expect. Now this is an electric field here. No, this is not a magnetic field. So I've just got a diagram here of a positively charged plate and a negatively charged plate, and I've got the arrows indicating the direction of the electric field, which is away from the positive towards the negative. Okay, so now that's always considered to be a uniform electric field. If you go and have a look in my textbook or any source, you'll see the field between two charged plates is considered to be uniform. Okay, but let's have a look at a magnetic field now. I've got here just a magnet of some sort. It doesn't matter what it is, with a north and south pole. Now the direction of the field out of the north is, as I've indicated with the little arrows, and then over here I've got the opposite pole, and the field is into the south pole. Okay, so the field is the direction an isolated north pole would move, or the force experienced by an isolated north pole in the field, which is away from the north and into the south. Up here, the definition of the direction of an electric field is the force acting on a positive test particle or test charge in the field. So a positive charge would move away from the positive towards the negative. So that's the direction. But we don't know with the magnetic field what's going on in between. Now you could assume it's going to be uniform. We do for a lot of experiments. But in the earlier experiments, what I've done is this. I've brought the magnet, we have the magnet really close. So as I showed you, a little channel with the magnets only a centimetre apart. We can assume it's fairly uniform between the magnets. After all, you're not shifting the wire in the original experiment. So even if it's not uniform, at least you're not changing the magnetic field about the wire, the current carrying wire. Okay, so let's move on. Now this is the setup I'm using for the demonstration or the little experiment we're going to do. I'll just go through some of these bits and pieces, but you can see I've got some magnets there on a pan with the a little scale. I'll show you a couple of these things. Look, I'll just go back to this image here. What I've got is this. I'll just show you this. We've got a little piece of aluminium channel, and that's just about 36 millimeters wide. I just bought a piece of aluminium from Bunnings and just bent it into a little U shape, a square U. And so I can put magnets either side of that. So there's a north pole of a magnet that just sits on that side, and on the other side would be another magnet, and they'd hold themselves together. Now, I'm not going to show you the north and south together, because chances are they'll slip off and crash into each other. And that's a good point here. The number of times I've cut myself on these magnets, and you end up with blood blisters because they come together extremely fast. Students in my class, I have to keep warning them, don't get your fingers in between. So that's a good point you can mention in your risk management section of a report. Be careful of these things. They come together with a real bang. So that's the setup for the magnets. The little bit of ruler you can see there is just this thing here. All it is a piece of ruler. I just bought a 1 meter ruler from Officeworks. Now that's about $4. I just cut off a little chunk off the end, and I've wound some wire around it. Now in the image you'll see there's a wire. I've done 10 turns of this wire here. Now this is just wire from JCAR. It's 0.4 of a millimeter in diameter. It's enameled copper wire, and I think that costs $8. So that's that. That's this with the 10 turns of that copper wire around it. You'll see a couple of other things in a minute. Look, I did measure the width of that ruler, because you'll need to know the length of the loop in the field. So if I measure that, you might be able to see on the screen. Yeah, you can see it there. 2.63 centimeters, or 26.3 millimeters is the width. And so I've got 10 turns of that wire in the field. A couple of other things you'll see is this thing here. It's just a variable resistor, or it's a potentiometer from JCAR. Now that's, I think, about $18. It's a 5 ohm one. It's really good for this sort of experiment. Wire wound, it can take a fair current, but it will get hot. And you've got a center tap in the middle, and the positive and negative hooked up to your power supply there. So that's a really useful thing. You might have the big rheostats in your classroom. They're usually 10 to 20 ohms. They're just as useful, but these are cheap, easy to get. A lot of lab managers have said to me after these talks, I'm so glad you talked about getting cheap equipment, or getting low-cost equipment, or no-cost equipment really, because schools' budgets are really stretched, and you're doing a whole lot of different physics pracs. It's handy to get the stuff fairly cheap. Okay, so let's go back. Now, so that's the setup. You can see I've got the aluminium with the two magnets on a electronic balance, and you can see a little piece of paper. Now I just printed off from the internet a piece of ruler, and I just stuck that onto the plate. Now you'll notice I've got a little piece of copper wire just stuck under the sticky tape there, and that's my pointer. You'll need copper wire. Don't use a paper clip or anything, because it'll be attracted to the magnet. So just be careful with that. So that works pretty well. Okay, the other thing I should have showed you was the, I'll just go back and show you this thing, the voltmeter, or the multimeter that I use. Now, you just got to be careful to get it connected up to the right terminals, and I'll go through that in a minute. Now, that's a dear one from JCar. They're, I think that was about $30. You can get them, you know, for $10, but the JCar ones seem all right. I haven't had to send many back. A couple, the batteries seem to go flat too quickly, or some don't work. The JCar have been happy to take them back. Okay, so let's go back. Now, I'll move on and just go through the logic behind all of this. Now, what we're trying to do is work out the force acting on a current carrying wire. Now, I've said at the top here, you can work out the direction of the force using Fleming's left-hand rule, and that's if you are using this textbook, my textbook, that's on page 195. Some books will call it the right-hand palm rule, but either are okay. They're the same thing. In fact, there's other rules as well, and they all make sense. But basically, the two magnets are placed either side of that aluminium channel. Like I said, you can see this grey line through here, and that's the piece of aluminium I was telling you about before. And I've drawn the field lines in B across there. Now, there's the piece of wire that I'm going to use, which is just the bit of wire, wherever I put it, this bit of wire, which will be at right angles to the magnetic field. So you can see I've got it there coming out of the page, or out of the screen towards you. Now, if you use your hand rule with a current out of the page here and the magnetic field across the page from left to right, I use the Fleming's left-hand rule, and we get a force directly upwards. But if you want to use your right-hand rule, the palm rule, it'll make this, you'll get the same answer. So the force is up, which means it's the wires, the magnets are being pushed down according to Newton's third law. If the force on the wire is up, there's an equal and opposite force down. So that downward force increases the scale reading. Okay, so the scale reading is a measure of the force on the wire. And so now I've got 36 millimeters apart. That little channel I used is 36, only by accident. It's pretty hard to bend to whatever you want, but that seems like a nice sort of a number, somewhere between, I'd say, you know, 30 and 40 or 50, something like that. Seems to work pretty well. Okay, so just going back to the setup, looking directly from above, you can see I've got the multimeter in there. I'll go through the terminals in a minute in a separate photo. There's my piece of ruler with the 10 turns of wire and the little pointer. The magnet, so the north pole is just here where I'm pointing, and the south pole is there. So the magnetic field is across like that, in that direction. Okay, now I can get the position of the coil, or the wire rather, anywhere between 0 and, well, actually anywhere between about 5, because it's fairly thick to take all those turns of wire going across. Okay, and that's about it. I've got it in a clamp. I actually used an aluminium clamp and stand with a plastic base, but you could use steel as long as you don't, well, try and use plastic if you can. Try and use aluminium if you can. Okay, now there's my piece of wooden ruler that I was telling you about. That's just a close-up shot. You can see the 10 turns of the copper wire. I just cut a little groove out of the end with a hacksaw, both ends, wrapped 10 turns around. Now the length of the wire is around about 2.63. It's hard to get it exact, but that's about 0.0263 meters, and there's 10 turns of it. So the total length of the wire in the field will be 0.263 meters. And you can see here's what I said, 10 turns of the copper wire. Okay, and
lastly, for the setup, this is just the multimeter. Now you'll have different multimeters to this. Some of you might have this one, but they're all basically the same sort of idea. There will be a socket called 10 amp. Now we're going to run this at about 1 amp. If you use, there's probably, you'd have maybe a 200 milliamp scale. You could use that, but that's no good if you're going up to 1 amp. So you put it in the 10 amp, so the red goes into the 10 amp socket, and the black will go into your the COM socket, which is treated as negative, and have it clicked onto the amp scale and not the milliamp scale or anything else, and the reading will be an amp. So here it is here, 1.00. Well, looks like it might have been a 5 or something. It's caught, a photo caught it in between fluctuations. Okay, that's that. And now the next thing is, before we do the experiment, what do we expect? So when you're writing this up, you'll have to talk about, some expectations, or what's a little bit of theory behind it. A couple of things you've learnt this term, or this in this unit, excuse me, will be Newton's law of universal gravitation. That's this one here. So big G times the two masses divided by r squared. So that's an inverse square law. You can see it here. If you're talking about gravitational field strength rather than gravitational force, gravitational field strength is also inverse squared relationship. Now the other one you've been studying will be Coulomb's law. The force between two charged objects is equal to a constant. Now I've just called it K because just to simplify it here, times the product of the charges divided by the distance squared, separation distance squared. So again, that's an inverse square law for force, and for the electric field strength, it's just also an inverse square relationship. Now the other one you did possibly in Unit 2, if you were talking about light, was the relationship for the intensity of light and distance. Okay, and the formula, I'm not putting it here, but would be I for intensity is proportional to 1 on d squared, the distance you are away from the source of light. So light intensity is also a inverse square. Look, it seems like that's almost a universal law of nature that we have an inverse square relationship. So I think you could reasonably expect that something like an inverse square is going on, but that's what we're trying to find out. Okay, now if it was inverse squared, the further you got away from the magnet, now this is, let's say this is the left-hand magnet, the further you got away from it, the magnetic field strength would decrease, of course. Okay, so now it'd be an inverse square relationship. Now, you could also try inverse cubed. It'd just be a lot sharper here. Okay, an inverse, and 1 on x to the power of 4, which it could happen, it could be, would also be similar, but it'd be much sharper like that. Okay, and of course an inverse, just a straight inverse, would be the same, but not quite as sharp as that. But let's assume that it's inverse square, just for the purposes of this discussion. Now on the other side, you've got the other magnet. So here it is here. And so it's inverse squared from the other side. Okay, so across the middle, if you like, there's the first 16 millimeters. And then you've got another 16 millimeters to the other magnet. Now, if you think about it, in the middle here, look, that looks fairly uniform. So it's not unreasonable to say that in the center of the field between the two magnets, it's quite uniform across the middle. Okay, now if these magnets were even further apart, this would be even a shallower angle. It would be quite flat across the middle, and it would be uniform. It'd be weak, but it'd be uniform. Okay, near each pole, look at it decreases in that inverse square relationship quite markedly, really.
Okay, so all we could do is put these two together. Let's imagine they're not too far apart, but let's put them a little bit closer like this. Okay, so if they overlapped, if their fields overlapped a lot more, you'd have that sort of setup. Now, magnetic field strength is a vector, but you can add, at any one point, you can add the two fields because they're in the same direction. I showed you before the arrows went from left to right. So in the middle, or anywhere, the fields are in the same direction. So you can just add them together to get the magnitudes. So here, I'd just have that magnitude from the orange and that magnitude from the blue, add them together, it'll be up here somewhere. So all the way along, at every point all the way along, you'd add the, if you like, the y displacement or the y value for each of them together, and it'd go up through here somewhere like that. Okay, so in fact I've done this using just on Excel, and that's what you get. So that's adding them together. So if we did have a inverse square relationship between the magnets, we should measure something like that. That's what we'd expect, something like that. If it's inverse cubed, it might go down steeper here and then flatter and then steep here. You'd have to do that for yourself, or find it out for yourself. Okay, so in other words, this is a bit of a prediction that it might look something like that if it's inverse square. That's the distance from the North Pole all the way across the 36 millimeters. Now, I've got some typical values in here. I know that each of those two magnets I was showing you before have a surface magnetization according to the handbook or the specifications of about 0.36 Tesla. So if you think you extend that up a bit, it might go somewhere up there. But it's in the order of, 0.2 to 0.4, somewhere in there is the surface. So that'll be heading up there somewhere. And the same on the other side. Okay, now those magnets that I got, those two, now they're from Aussie. I got them from Aussie Magnets. They were $13.20 each. And I'll go through some of the bits and pieces about them in a minute. But you can get them cheaper other places. Okay. Now what I'm going to do is let you collect your own data. What I'm going to do is take this pointer all the way across, and you'll get a reading on the scale, on the pan, or the scale reading on the balance. Excuse me. And I'll keep this at 1 amp. Okay, so I'll get started, and now you can hear me turn it on, and that's to say it's going. I'll zoom in a little bit so you can see what's going. Okay, so 1 amp, it's reading about 5.3. Zoom in, you can see it. You can see my pointer's at about 5 millimeters. So you'd record that as your first pair of data. 5 millimeters and 5.3 grams. Okay, now what I'm going to do is shift it across. You can see I've shifted the pointer across to 6 and then to 8. And you can see the readings, the scale readings are going down. 10. Now I'm going fast here because if you wanted to get this data, you could just stop the video and get the pairs of data. That's the intention, for you to collect your own data. Now I know I'm doing the experiment, but being able to record the data is important. And not everyone will have this equipment. And so depending on where you live and whether you have access to this equipment, you can just make use of this, even as a practice for plotting graphs. Now people from all over the world use my videos to collect their own data because they don't have access to this, especially if they're in a COVID lockdown and they're not going to school. This has been useful. So I'm up to 28, and you can see I'm very close to touching the ruler on the little bracket. So I won't go any further. Now I'm going backwards, that's 28, to get duplicate data so I can work out uncertainty. So you can record this again. That's 24 millimeters and 22. 2 millimeters, look, it's about 2.78. 20 millimeters, 2.52, and so on. I'll go back in twos all the way back to the start. Now, back at the start, it should be the same as it was before, but we've got the pair of data. And when I turn it off, it should go back to 0 grams, but often they don't. There's just a little bit of random error creeps in. Okay, so to 6 now, and there's one more to go, which will be 5, and there's the 5. I hope I haven't touched the magnets, but anyway, it's pretty close to what it was. Now I'll turn it off, you'll hear it click off, and it's going down to 0.04. So there's a little bit of error there, but that makes life interesting. Okay, so hopefully you've got the data if you want to do that. Otherwise, we'll move on. Now, what we need to do is to calculate the force. We'll use the force formula to calculate the magnetic field strength at every point, every 2 millimeters across. Now, there's the formula we're using, F equals BIL sine theta. Now, out of the textbook, it's page 197, but you'd be familiar with that. Okay, B is the magnetic field strength, I is the current in amps, length is the length of wire in the field, in meters, and so on. Okay, so now I put 0 equals 90 degrees because the wire was at right angles to the magnetic field direction, so the sine of 90 is 1. So the formula becomes F equals BIL. Okay, now I can rearrange that to get B equals F on IL. Now the force, if you remember before I said it's just the scale reading, so that's the mass in kilograms times G, which is the acceleration due to gravity. Okay, so it looks like this. B equals mass in kilograms times 9.8 divided by I, which is the current in amps, so I've got it here as 1, times the length of wire. So it's 10 turns of wire, and each turn is 0.063. Oh no, that's not right, it's 0.0263. I should fix that up, so take no notice of that. That's a typo. The formula, the calculations are correct. I just made a little mistake there. So it's 0.0263. In other words, 26.3 millimeters. And let's move on. Okay, so look, I fixed it up here. That was just a silly mistake. So B at the 5 millimeter mark, if you remember, is about 5.48 grams. Divide by 1,000 to get to kilograms, times the 9.8 to convert to newtons, and divide by 1 amp times 10 times 0.0263. And that comes out to about 0.204 Tesla. So here's my table now. Now I'm not going to show you all the results. That's for you to do. So I'm not going to do all your work for you. I've done this for myself, but I've just got 5 sets of data for the first 5 readings in there. And now I've done this 3 times. Now look, this is not exactly the same data as from that video. So I did this experiment a second time, and in the second case I did it in triplicate just to check what's going on. But the idea is the same, but I didn't want to use the same data as you'd get off the video, because I don't want to, like I said, that's for you to do, and I'm not going to do all your work for you. So I've converted each one of these scale readings in grams to a magnetic field strength, or flux density if you like, in Tesla. And I did the first one on the previous slide, it was 0.204. So I've done that for each of those 3 readings, and I get those 3, and then I've averaged them. And I've done all the way down for up to 12, but of course I did it for up to 30 millimeters. Okay, so I worked out the delta value, which is the uncertainty, the absolute uncertainty. So I've taken the max from the min. So I've been through these and I've taken max from min. So max is 0.204. You've got two versions of that, minus the min, which is 0.202. Subtract them and divide by 2, and you get a number there. So I've done that for each pair. But if you've only got two pieces, you just take them one from the other, make them the absolute value and divide by 2. And then I've converted that to a percent, which is just the absolute uncertainty divided by the average value times 100. So 0.0009 divided by 0.204 times 100 comes to 0.5%. Now look at that uncertainty. That's pretty good. Something around a couple of percent uncertainty is pretty good for particularly that experiment where it was so hard to get the reading of the position of the coil or the wire loop. So that's our data. Now the next thing to do would be to plot this. So you plot D along the x-axis. That's the independent variable, and then on the y-axis you'd plot the dependent variable. Okay, now let's see what happens. Now that looks very, very much like what we were saying before with the inverse squared. So maybe the relationship is inverse squared. You'd have to compare this to an actual inverse square relationship and see how you go. But that's plotted nicely. Look, you're getting a beautiful smooth curve through there. When I first did this, I thought this is fantastic. I can imagine students doing this, and I can imagine what my students would think. They'd think this is fantastic. They can see an A plus coming up immediately. And you'll notice the midpoint is somewhere around about here, about 17 to 18, which is halfway across the distance between the two magnets. So that looks pretty good. Okay, now, so you've done that, and you might say, well, that looks almost like an inverse square relationship, and you'd finish up writing up your prac by saying that you've got that. You might do some error calculations and talk about it a bit more. But if you want to take it a lot further, now, I'm not saying you normally would, but this is where you can really shine with this by taking it the extra step and having a look at the experimental values, not just having a look at the theoretical values. Now, you don't know what the theoretical values are because you don't know what the value is at the face of the magnet, magnetic field strength at the face. I said to you it's about 0.36, but that's just for that particular magnet that I'm using. So let's have a look at how you'd calculate it theoretically. Now, I've said here theoretical calculations. Now, there's the magnet. Now, that's the side-on. That's the side-on version of or view of the magnet. Okay, with the North Pole one way and the South Pole on the other side. Now, I'll give you a reference for the calculations in a minute, but I've labelled this. We've got these labels: L for length, W for width. Now, you might think, well, that's for the height, but don't forget, you could think of these magnets as just lying flat. So that's the width, and D is for depth. So you've got those three. Now, with the magnet I'm using here, I got this, like I said, I got this from Aussie Magnets. It's 40 millimeters across there, 40. The width is 15 millimeters, and the depth is 8 millimeters. So I can use those values in meters in any theoretical calculation. Now, X is the distance you are away from the north face. Now, this formula will apply for the south face as well. There's no difference. And let's have a look at it. Now, it's a frightening looking formula. But if you go to this website here, where I got the formula from, they're the biggest, they're German manufacturers of these magnets. So they've provided the theory for anyone buying this type of magnet. And it depends on the grade of the magnet as well as the coating and all the rest of it. But if you get these from a good supplier, they'll tell you what grade they are. and certainly from Aussie magnets, the ones I get, they do. The ones from Bunnings, you can buy these from Bunnings, not this exact one, but they don't tell you what the surface magnetization is, but you could look up a website and you get close. But anyway, this part of the formula here is the factor for the North Pole, and then you subtract the magnetic field strength due to the South Pole, because after all, when you're at a position here somewhere where the X is, you're getting a field from the South Pole in that direction, but this South Pole is not far away. I mean, you've got fields leaking all the way around the sides. So this formula actually gives you the North Pole value at a particular point, but subtracts the contribution from the South Pole because it's in the opposite direction. So that's all that formula is getting at. Now BR is it's a reference value. If you go to this site, you'll see it. You find out what it is. It's roughly related to the surface magnetization of the magnets, and it'll explain what all the X values are. It's not just the distance from the face. It also takes into account a tiny nickel coating that's on here, which is 0.06 of a millimeter thick, but that wouldn't make much difference for us. Okay, so you just plug it all in. Now I just typed all that into Excel, made up a spreadsheet and did it, but you can go to this website and put all these values in and then do it for X for 5 millimeters, and it'll give you an answer, and then do it for 6 and 8 and 10 if you like it. That's probably the easiest way to do it, and you can use that as the reference. Okay, now moving on, here's my distance values across the between the two magnets. Here's the theoretical value using that formula. Okay, so I've done it for each one here because I did it all the way through to 36. I had to add the contribution from the left magnet, and then add the contribution from the right magnet as well, because they're both in the same direction, so they add together. And then I've written down here the experimental values that I got off the video. Now you look how nice and close they are. They're roughly the same. I mean, you know, to the second decimal place, they're pretty much the same. Now the question is, how close are our experimental values to the theoretical value? How would you write about that? Now, it's a bit tricky because these are power relationships. You can't just average, but look, here's a few suggestions. That's the point I'm making here. How can you do it? What would you say if you're doing it in a report? Okay, you could compare the averages. So in other words, the average of all your experimental values with the average of all your theoretical values. Now I did that, and here are the two averages. That's for each distance across, and it comes out to a difference of 0.006 Tesla, which is about 4%. You could say, well, that's all right, that's less than 5%, so maybe it's accurate. But I don't know how fair that is for inverse power relationships. There must be a better way of doing it. And if you're in biology, if you also do biology, or the biologists would do this. If they've got two sets of data, now it could be the number of cane toads in a particular paddock compared to another paddock, or the growth of radishes in one box compared to another box, depending on fertilizers and stuff. They have ways of comparing it. Now they do a Ttest. Now this is more or less in their syllabus, so they're familiar with this. They in Excel they would do a paired Ttest for 15 pieces of data. So there's two lots of 15. I mean, this is called the degrees of freedom, but it tells you there were it tells you there were probably 15, and they're paired, so there's 30 readings. It gives a T value of 0.43. The critical value is 2, so the T is less than the critical. So you can make a statement about whether the two columns of data are identical or how close they are, whether they're different or the means are different. And the p-value is 0.67 in this case, which the biologists would say it's greater than 0.05, and they can make this statement here. Now, I won't go into that, but in simple terms for us, there's no significant difference between the experimental and theoretical. Okay, by taking into account the variation in all of the results, not just the average, but the variation for the whole set, you can make that statement. But again, is that a fair comment for inverse power? Now, in physics, this is what I'd suggest we do. Now, if you plotted the expected value against the theoretical value, now if they are identical, you get a lovely straight line. So this is what you'd get in theory. Oh, wait a minute, before we do. I've plotted the experimental versus the theoretical. Okay, and you'll see here my experimental data is the blue one, and my theoretical is just is the orange. Now you can see how close they are. When I first saw that, I thought this is absolutely fantastic. Look, the shape is almost identical, out by just a tiny fraction. Now that could be a systematic error in measurements or who knows what, but there's some systematic error going on there, or maybe it's an error in the interpretation of the formula. And I'll just put some data here. Oh, sorry, the top one is the theoretical value. Of course, it's higher than the experimental. So theoretical value, now I tried fitting a curve to it. You can't just fit a power relationship. You could for the first half, but then you'd have something funny going on here. So I just tried fitting a parabolic relationship to it, and with an x squared, with x equals 2 or 2 factors. And it gave a pretty reasonable line for a prediction as the trend line there. In the blue, you can see the dotted blue line. R squared value of 0.996. Now that's fantastic. So you could almost say the experimental or the theoretical data follows this parabolic curve like that, and the experimental data does the same sort of thing. Okay, slightly different formula because it's shifted down effectively, so it's it's shifted a little bit in comparison to the theoretical value. And look, I've worked out a turning point for both of those. I think I didn't write it in there, but there's a turning point for this which is about the same, somewhere around about here, 16 millimeters or so on. Okay, now like I said before, if you plotted the theoretical along the bottom against the experimental, and if the data was equal, was absolutely the same, okay, identical, you'd get that. Now ours aren't identical, but they're pretty close. But if it was 1:1 correspondence, the relationship would be y is equal to 1 times x. In other words, the experimental was equal to the theoretical, and your r squared would be 1. In other words, all the values are on the line. Okay, the equation is a great fit, perfect fit for the data. Okay, let's have a look at what happens when we plot our data. Now keep that in mind. That's what it would look like if it was perfectly 1:1, and here's ours. Okay, you can see it's not exactly 1, but it's very, very close. And the r squared is so close to 1. A little bit of offset here. Okay, cuts through here. So that's possibly a bit of systematic error. We don't know. You'd have to explore that more, but you can talk about that. Now you could add all sorts of error bars and that to this to see how it goes. But that's basically how you could write up this experiment. It's a fabulous experiment. It works really well. There's so much to talk about, so much room for discussion, and I wish you well if you do it. So that's the end. You can see a little bit more on my website. I listed some other pracs, those mandatory pracs I was talking about, and so on. So that's it. Okay, over and out. I'll stop there. Au revoir.